everyone, and welcome to another math tutorial. This video is the second video in a series on chapter 1. This video is titled Measuring and Constructing Segments. However, we're not going to really get into constructions today, constructing of segments. I'm going to save constructions in this unit for a separate video that will accompany this playlist. But let's get right into this lesson's video. First thing we're going to start out with is just a little bit of vocabulary. In the course of geometry, you're going to come across a lot of postulates or axioms or theorems. Our text uses the word postulate over axiom, but they could be used interchangeably. Simply put, a postulate is a rule in geometry that is accepted as true without the need to prove it. A lot of work will be done in this course on proving theorems and writing proofs, but for postulates you don't go through that process. It's just accepted that it is true. Okay, we're going to look at our first postulate of the course on the next slide. Okay, this first postulate is called the ruler postulate. I'm sure everybody at some point in their life has used a ruler to measure the length of something. Or if not a ruler, maybe you've used a tape measure to measure the length of something. And so this ruler postulate can be associated with these two measuring instruments that we all probably have a little bit of basic experience with. So the ruler postulate says that the points on a number line, okay, so points here are on a line, can be matched to real numbers or coordinates. And I'm sure we've all seen this or come across this in a past, like, you know, maybe you've got here a line and points and possibly there are marks here on the line and there are numbers under those marks, etc. And so the points on a line can be matched to real numbers or coordinates, and that's what we mean by that is we've got numbers there, coordinates. Now this ruler postulate says that the distance between points A and B on a line is the absolute value of the difference between the two coordinates. So in other words, we can just find the difference between these two values, whatever their values are, and then to ensure that that difference is positive, we take the absolute value of that difference. Okay, let's see this on an example. Okay, back to our ruler postulate, and here I've got a ruler as an example. Oftentimes when we use the ruler, it's very commonplace if I want to measure the length of a line that I put the end of the ruler on one end, and then I can simply just read the scale of the ruler out to the end and I know how long that segment is, right? Well, this ruler postulate says that you can still find the length of the segment. Your ruler here doesn't have to be positioned so that 0 is on one of the endpoints. So here we've got this ruler placed below the segment. We can still find the length. And so what we need to do first is figure out what numbers or what coordinates match these points. So here I've got point S right here. S looks like it's at 2.0. And then I've got point T here, which looks like 5.4. And so the length of this segment is going to be the absolute value of the difference between these 2 points. So I can do 2.0 minus 5.4, which is the absolute value of negative 3.4, which is 3.4. Or, and most of you would probably just do it this way, where you take the larger number minus the smaller number. And if you do it that way, the absolute value bars actually are not even necessary, because if we put the larger number first and I subtract, I'm going to get a positive number here, which is still going to be positive. So this is probably the second approach is probably the way you're going to do it. And if you do it that way, you don't even really need these absolute value bars. You can just simply subtract 5.4 minus 2 to get the length. Now, one thing that I didn't talk about in the last slide, so I'm going to go ahead and talk about it here real quick is just some notation differences. Obviously, when we're talking about the segment, and we talked about this in the last video, we talked about the segment, we use the notation that with the bar over the segment, right? When we talk about the length of the segment, we're just going to write ST. So notice the difference here in the notation is very simply that we drop the bar above the lettering. So when I did that in my work right over here, notice that I just wrote ST. I didn't put a bar over it. Same thing here, I just wrote ST. And so whenever you see the notation that way, when you just see the endpoints of the segment but no segment bar, it is understood and implied that we are talking about what's the length of that segment. Okay, our next bit of vocabulary is congruent segments. And congruent segments are two or more line segments that have the same length. Let's try a different marker than that one. So two or more line segments that have the same length. Okay. Now later on we're going to do some constructions and I'll teach you how to construct congruent segments. But again, we're going to hold off on that for a later video. So how do you say that two segments are congruent? What is it that indicates the two segments are congruent? Well, for one, you see the tick marks on the segments. So what I mean by tick marks is that little tick and that little tick. So those two tick marks mean that this segment is congruent to this one. And again, congruency means that they have the same length. The other way that you can say that two segments are congruent is with this notation. It's an equals sign with a little kind of squiggle on top of that, and that means congruent. So what I could say for these two segments is I could say that segment AB is congruent to segment CD. And so when I see that symbol, that tells me that these two segments have the same length. Okay, first example problem asks us to determine if the segment with endpoints A and B is congruent to the segment with endpoints C and D. So let's start by just plotting this out. So my AB points are at -5, 5. So -5, 5. That's point A. And B is at -2, 5. There's point B. And those are the endpoints of a segment. Now, when you plot points on a graph, please go ahead and label the points so we know what those points actually are. The next segment is CD, so we got 2, -4. So there is point C. And D is -1, -4. And those are the endpoints of a segment. All right, so determine if these two segments are congruent. So they're congruent if they have the same length. So what I need is the length of AB and the length of CD. Now on a graph, if you're on the tick or on the grid lines, you can just simply count. So AB is 1, 2, 3 in length, and CD is 1, 2, 3 in length. So they both measure 3. So are they congruent? I can say yes. AB is congruent to CD. Next example, same exact directions. We're going to plot out the points that make up the segments, and then we're going to determine if they're congruent or not. So point A is at 4, 0. Point B is at 4, 3. So there is segment AB. And the length of AB is 3 units, right? 1, 2, 3. Now CD starts at -4, -4, and goes to -4, 1. And there's C, there's D, there's segment CD, its length is 1, 2, 3, 4, 5. Okay, so the segments are not the same length, right? CD is longer than AB. So are they congruent? Answer is no, they are not congruent. Okay, one final example with the same directions. Determine if these segments are congruent. If you're following along at home, it might be a good idea to just go ahead and hit pause on the video. Try this one on your own, and once you've made your determination if they are or are not congruent, then you can press play and you can check your work. But here we go. Plotting the points A, B, so I've got -1, 5, and 5, 5. There is segment AB. The length of that segment, 1, 2, 3, 4, 5, 6. And then our next segment, CD, so C is at 1, 3. D is at 1, -3. So the length of that, 4, 5, and 6. So CD is also 6 units in length. So yes, segment AB is congruent to segment CD. Now we will at some point, just not in this particular video, we will at some point give you some exercises like this where the lines are not simply horizontal or vertical, but the lines might be slanted or diagonal. And you'll still do the same thing, but finding the length is a little more difficult, so we're going to save that for another video. Okay, we have one more postulate in this section. It's called the segment addition postulate. It's something that you're going to use very often in this course. You're going to see it show up quite a bit. And it's quite frankly, it's probably something you've used already, but without giving it a name, it's just something that you know how to kind of innately do. Essentially, the segment addition postulate says that if you have a point B, here's our point B, and it's between points A and C, then what this says is that the length, right, the notation-wise, this means length, that the length of AB added to the length of BC is equal to the length of AC. Okay, so we can take this little piece plus this little piece, and it gives us the whole thing. Okay. The second statement just says the same thing, but in reverse, and we'll talk about that a little bit later as well in this course. But that essentially is segment addition postulate. Let's see a couple of examples of this played out. Okay, here we're asked to find VW. VW is the length of the entire segment. And so according to segment addition postulate, VW should be equal to this piece, VU, plus this piece, UW. And so if I substitute those values in, we have VW is equal to, so VU is 30, UW is 45. So VW has a length of 75. Okay, another example. Again, we're asked to find VW. Difference here is that VW is not the length of the entire segment. So let's write a statement, and I'm going to start with the length of the entire segment, which in this case is VU. VU, the entire segment, should be equal to this piece, VW, plus this piece, WU. Now I've got two values here, the 31 and the 8. Let's plug them into the correct spots here. 31 is the length of V to U, so that's going to go here. VW is what we're trying to find. We don't know that. And WU is 8. Okay, so now we have an algebra equation, very simple one that we want to solve. We're just going to subtract 8 from both sides. we do that, we get 31 minus 8, which is 23, equals VW, or if you prefer, VW equals 23. Okay, our last example of segment addition postulate. We're asked to find the value of x and AC if AB is 4x plus 5. I'm going to write some of that on the picture here. AB here is 4x plus 5. BC is 13. And AC, which is all the way here, is x plus 27. And if you want, we can certainly do this, make it a little more clear what lengths we are talking about. Okay, I'm going to start with a statement relating the whole thing, which is AC. AC needs to be equal to the two pieces, which are AB plus BC. Okay, so again, what I'm saying is all the way from A to C is equal to this AB piece plus this BC piece. Now let's plug in all of our quantities. AC is x plus 27, AB is 4x plus 5, and BC is 13. I have some like terms here, so I'm going to go to x plus 27 equals 4x plus 18. I'm going to collect all my x's together, so I'm going to subtract x from both sides. At the same time, I'm going to bring my numerical values over to the left-hand side, so I'm going to subtract 18 from both sides. So x is canceling there, 18 canceling there. So 27 minus 18 is 9, and 4x minus x is 3x. If we divide both sides by 3, end up with x equals 3. Okay, so that checks off finding the value of x. Now we need to find the value of AC. And AC is equal to x plus 27. So if AC is x plus 27 and x is 3, replace the x with 3. So AC is 30. Okay, that concludes this video, this second lesson in chapter 1. If you have any comments or questions, please leave them below. If you found the video helpful and you enjoyed it, if you liked it, please support the channel by giving it a thumbs up. I'd like to thank you for watching this video, and I'll see you in the next one.